Okay, so another application that we can think about is the linearized KdV equation. Okay, so this will be dt b plus dx third derivative b 0 b x 0 equals b not x. Okay, this is for tx in R. Okay, so applying the same argument that we used with the Schrödinger equation, we can transform the differential equation. In this case, we will have that dt b psi t transform will be equal to dt b transform psi t. Okay, this will be equal to transforming minus dx third b. Okay, transform psi t. Okay. Okay, and if we transform this, we will obtain 8 pi third it psi third. Okay, and this we have to multiply by b transform psi t. Okay, so we just did the same that with the Schrödinger equation. Okay, and the same will happen with the initial condition. This will be transformed, no change. So then we can say, if we resolve the differential equation, the ordinary, we can say that bxt, okay, the solution is a b, is going to be equal to the anti-transform of 8 pi third it psi third multiplied by b naught transform, and then anti-transform all this. Okay, this is going to be equal to st convolution b naught, where st has to do with the anti-transform of this part. That will be st, it will be equal st of x, okay, will be equal to integral of minus infinity infinity e to pi I x xi e 8 pi the third it psi to the third d xi. Okay, so and we can say that this is just like a notation like we did, that this is pt multiplied by b not x, like what we did with the Schrödinger equation, that we in this part we say that we had e to the Laplacian t. Okay, this is just a notation. This will be the representation of the solution in terms of the Fourier transform. So this is the integral st, and one can can change variables, and we can make that st will equal to 1 over cube root 3t I x 3t, where IA is the Airy function, that is AI of x is equal to 1 over 2 pi integral minus infinity infinity e I xi x plus xi third over 3 d xi. Okay, so recall that in one of the last videos we talked about the proposition that said that if you had a oscillatory integral of this type, um, it will be in L infinity. Okay, so combining that with the change of variable, we have that the norm infinity of St will be less or equal than C absolute value T minus 1/3. Okay, so this St that is part of the solution, it will be bounded. This is norm infinity now because the Airy function is bounded by the it's in L infinity. So we can also bound the derivative. Recall that we will say d beta x will be the beta derivative in the, let's say, spatial dimension. Okay, or that we can call it d beta, or as we use in the Schrödinger equation in terms of the Laplacian, and the Laplacian derives 2 times, so we will say beta over 2. Okay, so this will be d beta of my function will be equal to, okay, so 2 pi absolute value of psi. Here I have to put the parenthesis, this also, beta f transform psi anti-transform x. Okay. Okay, so we had that st norm infinite is less or equal than a constant c t absolute value 1/3. And one can prove also if you have beta between 0 and 1/2, then absolute the norm infinity of d beta x would be justified. We get norm infinity is less or equal than c absolute value t minus beta plus 1 over 3. Okay, so using Young's inequality, we can bound dbx bt b0. Recall that we defined this as the solution, the KdV linearized equation, and we can bound this with the norm infinity, which will be equal to d beta x st convolution b naught. Okay, is also norm infinity, and okay, so we can bound this a constant absolute value t minus beta plus 1 over 3. It comes this part from here, and okay, and as we're using Young's inequality, then we will have this bounded b naught norm 1. Okay, so we will have the homogeneous derivative beta bt of the solution bt multiplied by b naught bounded by this factor, the constant multiplied by the absolute value of t that came from here, and then using Young's inequality we will have the b naught, the initial condition, norm 1. Okay,